Today we are going to continue with ESP pumps, and we are going to try actually to do an example. I uploaded an Excel file in Onyx Learning, so we are going to try to do it together in class. And for that we are going to use the case. I found enough data on the internet of the Peregrino field. It's a field offshore Brazil. I will give some more information just in a second. And why, there are multiple what we call, I guess you have seen some lectures about it, are artificial lift methods. Okay. And there are actually many methods that can be applicable, and the idea is to give more energy to the reservoir fluid to be able to take it all the way to the processing facilities, to be able to take it to surface. And among these methods, the most famous are gas lift, or the most widely used. Gas lift, we have electric, submersible, pump, or abbreviated ESP. Okay, but there are also some other methods that we are going to talk today. The lecture is about the ESP. Also, the intention is that is something that is used offshore, okay, because it can be used for high. Remember, offshore wells are usually high capacity wells, the wells that produce, that they pay a lot of money. So they can be used for high rates, the same thing as gas lift. But there are many other methods that are for lower rates and that are more applicable for onshore wells. But our focus is on offshore, so I'm not going to talk about them too much, but you should know at least that they exist. And we have PCP, that's progressive cavity pump. So progressive cavity pump, that's the way it looks like. Show what happened here. Okay, it's kind of a pump that is a screw that is rotating, and the fluid is passing from one cavity to the other. And there has usually they're made, this part that is gray is made out of rubber, and the inner part is made of metal. Okay, but the problem is this is very good for highly viscous fluids, okay, when the viscosity is very high, but the problem is that it's usually for low rates, and that's why it's more common in onshore systems. Very heavy oil, very viscous oil, like for example in Venezuela or in Canada, they use very much these pumps because they can deal with no issues with high viscosities. Then we have typical rod pump. Okay, I guess you have seen this kind of the image, or was the image of the oil industry for quite some time. Okay, just that system. Okay, bean pumping, and it's basically a cavity that when it goes up is filling the cavity, and when it goes down is actually pumping the fluid up. Okay, it's basically based on, these two are based on a positive displacement principle. And actually we could do some examples about it, but I don't think there is enough time. And also this is for low rates, low Qs, and PCP is actually slightly higher rates than rod pump, but still low rates compared to ESP. And then there is another method called jet pumping. It's not so used, it's not so popular. I think I have a picture here. And for jet pump, actually you need, can you see it okay there? Or the screen is, it's good enough, I think. So the red fluid usually is either liquid or it can be production gas. So you pump it down with a compressor at high pressure. You pump it down, and then actually it enters through a very restricted, through like a throat, okay? It has an expansion and converging section, okay? And in this section, when the fluid goes so quick that the velocity goes down very quickly, okay? The pressure goes down very quickly. And as the pressure goes down, so that is kind of sucking all materials to this low pressure point. So the fluid in the reservoir is getting sucked by that stream. So in this case, it's going out here and into this throat, and then it's kind of going up through the so maybe that's, let me show you a slightly less complicated diagram. Okay, it's called also ejector, or it's called Venturi type. So you have a power fluid, high pressure. When it goes, and high energy, when it goes through this small point, then the velocity increases very much, and due to the Bernoulli effect, the pressure decreases. Okay, velocity increases, pressure decreases, and as the pressure decreases, this causes a sucking effect. Okay, and here you put a connection to the reservoir fluid, and those fluids are being mixed, and they go all the way to the surface. Okay, and there are different ways to put it. Here I found a picture of a horizontal completion, but it's actually put in the, it's actually installed in the vertical part of the well. Okay, where you see here there is a line coming down, and that's the high pressure line, and then here you have this device that is sucking fluid from the reservoir, and then actually both the mixture is going up the tubing. Okay. And jet pump is also not so common offshore. Really, the most common are gas lift and ESP, and the other are for land. As I told you, gas lift could be used also not only inside the well, but also some parts of the production system, especially risers. Electric submersible pump, the principle of pumping is very similar to, it can be installed either also in the seabed, or you could use a compressor when you have mostly gas to boost the fluid. And jet pumps are also sometimes used in the, I don't think there is any installation subsea, even though there are plans to install these pumps subsea, but most of them, they are installed in the topside facilities, in the platform, okay, to reduce the pressure before the separator. And each one of them is kind of a small, needs a small lecture, so I'm not going to cover all of them. Okay, just for your information. So now let's go. I decided to stop. I know there are some things that you are missing in pumps, okay, but let's go right away with the case, the application case, and show you what is kind of the issue there. And then slowly we're going to talk a bit more about the details and the performance of the pump. So we're going to talk about the Peregrino field. That's the field for which I have found data. Okay, the Peregrino field is a field offshore Brazil, located actually south of, I think someplace here is Rio de Janeiro. Someone here from Brazil? No? Someone has traveled to Brazil, has been to Rio de Janeiro? No? No? Okay, I think it's someplace here, okay? And the field is just offshore. I think the water depth is close to 100 meters, and it's a heavy, it's like the API of the crude is 14 API, and the viscosity of the oil is something like 120 to 200 centipoise at reservoir conditions. The GOR is very low, it's something close to 100. And it has an aquifer that is giving pressure support and water reinjection. Actually, the water is not treated, because remember, to dump the water to the sea, you have to clean it up to a very pure level. So actually the water, they don't have these facilities in the platform. Did I put the... They don't have these facilities in the in the platform, but actually all the water they re-inject to the reservoir to keep pressure support. Yeah, so the how it looks like it's already in operation. I think it started in 2011. The operator is Statoil, and this is kind of the big pride of Statoil International. And the development concept is to wells drill from platforms, from true platforms, to two areas of the reservoir. I think I have a picture here of the reservoir. Okay, so that's kind of this part goes here and this part goes here, and they have producers and injectors drilled from the platform, and these are deviated and horizontal wells. They are deviated at the beginning, and then they have horizontal sections, and they are produced here, and in here they have just drilling equipment. They have also intervention equipment. They have the power feed or the power installation for the pump. They have this variable speed drive, but actually all the production is then pumped through flow lines to a FPSO, and that's actually where the processing takes part. Okay, so I think I have a picture here of the platform. Okay, and the wellheads, they are the Christmas trees, they are dry. Okay, and you have actually drilling module. The rig is going to position itself depending on which well. There is some cascade here. We have some Zen atmosphere. That's better for teaching, I guess. Okay, so here you have the generator, also power generator, but all the treatment is done in the main FPSO. So actually you have to pump all of this mixture of water and oil here, and then the water comes back for the injectors to go down. Okay. What else? So we are going to analyze one well from this field. We are going to check first how is it going to be, how to, without having any information about the ESP, which ESP we're going to put on the well, how to more or less to forecast how is it going to behave in the future, okay, and when are we more or less going to have problems. With ESP, something very important and very interesting, the typical life of ESP. Okay, ESP is, you have to think about like almost like a human being. Okay, if you say have a good diet, you do frequent exercise, if you live in a kind of a safe country, no crime, anything, the pump life, you know, is going to be, I would say, maybe 80 years. Okay, it's going to be 5 years. Okay, that's a relatively good life of ESP. But if the ESP then doesn't eat very well, you know, it's in a very highly dangerous country with crime and, you know, robbery, etc., then might have 2 years or even 1 year. Okay, 6 months is already very extreme, but that's more or less the range. But if you feel like the life of the field is going to be like 20 years or 30 years, then if you have to replace the pump, is going to last only for 5 years. Then you have to have already in advance an intervention scheme that you have to go and go to the wells and change the pump every 5 years. So that's why, in part, because the rig is in place and because the intervention is kind of done because you know that you have to do that in a regular basis. Okay, so that's a part also of the motivation. That's kind of a medium. Okay, it's not rare, okay, to have a pump that lasts only for 2 years. And something that really hurts the operation of the pump is frequent startups. Okay, start up and shut down, start up and shut down. So frequent startups and also shutdowns hurt, okay, the life of the pump. Okay, and we will see later some other factors, but basically remember that the pump is using a motor, an electrical motor, and every time you start there is a peak of consumption of this motor, and so that peak is really hurting. Every time you use the peak, it's kind of hurting the life of the pump. Also, something else is sand production. Okay, affects also in a negative way the life of the ESP. Yeah. Okay. That's how the completion looks like. ESPs, they cannot only be installed in a vertical section. In the old times it was like that, but actually now they can be installed in the deviated section. So that's how the completion looks like. Okay. And basically for ESPs you have, for ESP lifted wells, okay, there are kind of two ways to operate. Okay, one of them is liquid through tubing, okay, and gas through the annulus. Okay, and this is very typical for onshore fields. Let's do the picture, the drawing of our well. No class can be complete without a well picture. Okay, and you make you have access through the annular valve, through the annulus valve, and then what happens is that you separate. Actually, if there is some gas coming from the formation, you have a like you saw last class. Okay, they have a gas separator, rotary separator, and that sends the gas just in bubbles or in batches through the annular space and all the way. And what might happen actually is that the liquid, you have a static level, okay, and the gas percolates through this liquid, and then it occupies this space and is produced through the annulus. Okay, that's one configuration. If the P, let's call this P flowing bottom hole, is less than the pressure of the bubble point of the oil, okay, of the fluid that you are producing. So that's bubble point. And you will hear also some, in some, when you are in your professional life, you will hear like submergence, okay, pump submergence. You will hear the term pump submergence. Submergence, yep, okay. And it's actually the liquid level. What they do is they connect here an air gun, okay, something that generates kind of a wave, okay, a pressure wave, and this pressure wave goes down and it reflects up. So they measure whenever it hits the surface, it reflects, it gives a special reflection, and that's where they can determine the depth of this liquid level. Okay, and with the depth of the liquid level, you more or less neglect the gas that is circulating here. You say that is very small, and with the liquid level and the pressure in the annulus, you can determine the pressure and the suction of the pump. Okay. Now there is one kind of issue with this configuration producing through the annulus for offshore wells. It's actually, if you produce through the annulus, you don't have enough barriers to, remember all the time we have to have two barriers, okay? And in the case of the well, we have one big thing that is the downhole subsurface safety valve, okay? And we have to have the same in the annulus. So that's why until some years ago, people were not very happy about producing or leaving the annulus open without any packer, or producing through the annulus, because then they don't have this additional barrier. Yeah. So, but then came some people saying, okay, we can install an annular safety valve. Also, we can do exactly the same thing or something very similar to the subsurface safety valve. We can do an annular safety valve. To put it here, let's see which color do we use. Okay. It's actually something that allows passage, okay, through the annulus, but it's also protected, also has a hydraulic line. Whenever, if something happens up there, something fails, it's going to close. Okay, it's going to go to the fail-safe close position. Okay, so it's called annular safety valve, I think. Okay, and people really don't like it very much because it's an extra equipment that you have to maintain, that if fails you have to retrieve, that you have to take out the tubing to put it. So really people don't like it very much to use these annular devices, safety devices. Okay, and then there is another approach that is you produce liquid through tubing, liquid and gas, if any, through the tubing. Okay, and actually that is that you have the ESP and you have your packer, okay, your annular packer for like the barrier that you want. And then the fluid has no choice, but everything has to pass through the ESP. Okay, the fluid that comes here has no choice and has to pass through the ESP. Usually the gas, the presence of gas, it impacts very negatively the performance of the pump. Okay, at the end, if the pump was projected or designed to achieve certain enthalpy, for example 100 bar, when you have gas, it impacts very quickly. When you increase the amount of gas, this 100 bar go very quickly down. Okay, and it affects negatively the performance of the pump. You have more vibrations. The gas usually doesn't cool very efficiently the heat that the pump produces. The pump is producing heat, so also might lead to more failures, etc. Okay, so gas. Okay, you have the pump, that means performance. Okay, it can lift much less. Then you have vibration. Then also you might have cooling. Okay, decreased cooling is not as good as it is when it's liquid. So it usually causes more failure, more more frequent failures. And usually a number that you say, okay, what can we accept at the suction of the pump is a GVF, gas volume fraction. Okay, and this is the local rate of gas divided by the rate of liquid plus rate of gas. Okay, this is local. Remember that it doesn't have the bar on top of the G or the O, so this is local. Has to be less or equal than 0.3, okay, 30%. That's kind of, we say it's the maximum that is acceptable now by the ESP pump, but the pump has to be designed to take that. The rotor, for example, that I showed last class is not designed, it could not take 30%, not even 30%. So to avoid some of these issues, some people, what they decide is you say, okay, we are going to make a very quick fix. We are going to say that the P at the suction has to be all the time greater than a factor of security, a security factor, times the bubble point pressure of the fluid at that temperature. All the time, no matter what. I don't want to get any gas in my pump. Okay, And this is what these guys from Peregrino are doing. They say, yeah, all the time, let's say this factor you can put 1 point, you can put 10%, 5%, okay? If the bubble point pressure in the case of Peregrino, I think is 30 bar, okay? So I want it to be my suction pressure all the time, no matter what, has to be single phase liquid coming into the pump. And like that, I just solve the problem, no gas, these problems with gas, these problems with producing through the annulus, accumulation, okay? So, and that's actually what they're doing, and I can show you now the picture of the completion, okay? So in the completion, you have a horizontal section that is actually completed with gravel pack, and then you have the suction of the pump. It has also, you see here the cable that goes up from the top. There is actually one cable. Okay. There is actually this cable, red cable here. That's for the subsurface safety valve, okay, to keep it in the open position. And then you have a line that goes down, and that line carries the power to the ESP, the energy to the ESP, the electrical power, and also carries some chemical to avoid the formation of emulsion. We are going to neglect that for now, okay? But they analyze that the emulsion is a big issue, and that could cause trouble. And then the cable passes through the packer, okay, that is blocking the annular space, that is the barrier of the annular space. And then from here it splits into one power cable to the ESP, and then it goes further down to the suction of the liquid from the formation to inject this de-emulsifier agent. Okay. There are some other components there that, you know, let's not dwell too much on them. Okay, so let's open let's do kind of a design of ESP, okay, to see how much we're going to get with an ESP for our system.
Professor?
Yep.
There are some ESPs that are equipped with special modules that will accommodate more gas.
Yeah, I will show you some pictures. Well, I can show it right away if you want. Yeah, this here you have a picture of a rotor that takes more gas, is more gas friendly than a rotor that is not so. This is the rotor that you have seen, the impeller that you have seen last time in class, okay? Actually the fluids enter through the center and then goes radially, almost in 90 degrees to the peripherum, okay? This one cannot take much gas at all. Now, this case, you see that actually the passage is not in 90 degrees, but it's something smoother. Okay, it's like 45, and this helps very much with the gas. The problem is that this stage can lift much less pressure than this stage. Okay, so you need many more of that to achieve the same delta P.
And is it 30% also?
Yeah, these kind of impellers, they take 30% GVF. These very small, like 5%, no more than that. Almost no, these are made for almost no gas at the intake. Okay, so let's open the Excel. It's the version is called MT, and I have put here a lot of information. And let's focus only on on the equilibrium analysis that I guess you're already experts on that. Okay, because you have seen it so many times that you are getting fed up with the equilibrium analysis. So let's see the data that we have here and what is the plan. You more or less know already what is the plan, okay? You have calculated choke, and I told you that it's very similar to calculated pump, so you already have an idea what you have to do. So let's just to put you in the same page. So that's the data provided for this. That's the data provided for one well in the Peregrino field. And the reservoir pressure, that's initial reservoir pressure, so 231 bar, that's initial. It's going to go down with time, but not so steep, because we are injecting water, and because we are injecting water and there is aquifer. This is J. So this kind of rings you a bell that here is the equation that Q of fluid, okay, Q liquid is equal to J of liquid times PR minus PWF. Okay, I hope you remember that equation. It's linear IPR for undersaturated fluids. Then H1 is actually the distance between the formation, okay, the formation in that case, let's say, is down here, and the pump suction, H1, okay, and H2 is the distance between the pump discharge and the wellhead. So let's put that P1, H1, from, we can call it the sand face, okay, from where the fluid are coming in, from the sand face. And H2 is the distance from a pump discharge to a wellhead. And if you see the picture, really it's deviated well, okay? We're going to make a simplification, assuming that really this distance can be neglected, and I just care. So what will be H1 here in this drawing? Okay, one thing could be, so this is where I remember when all the inflow is finished, this point is the one that I choose for my flowing bottom hole pressure. Okay, so now this will be the starting point where I define this. All of these we're going to represent as an IPR, a linear IPR, and then we have all the way to the suction of the pump, right? So this distance will be H1, and I'm assuming just that it's vertical. While in reality it is not, but really it doesn't give any additional complication. Okay. Then we have the pump discharge will be someplace here and all the way to the wellhead. So again, that distance is H2. Okay. And I'm assuming that they are vertical segments. That actually the distance along the well is the same as the vertical distance. Then I'm giving the diameters of the two sections, and that's actually quite a big borehole, okay? And the diameter of the tubing is also quite big. It's 5.5, and this is 9 5/8 of the production casing. I'm giving the roughness. Remember, we need the roughness to do pressure drop calculations, and here we are not going to care too much about that. Already someone chose ESP for us, okay? So then we are going to verify if that's going to work or not. But for now, let's not pay any attention, okay? We have the density of the water is slightly higher because it has some salinity, it has some minerals, salt dissolved on it. Oil, 897, okay? That's the API, I think, of 14, should be. Then, this crude displays, I'm not sure if you remember some time ago, a long time ago, maybe 2 weeks ago or something, I told you that the mixture of oil and water, okay, or not mixture, but the dispersion, okay, displays sometimes this kind of behavior. When that will be the water fraction, that will be the viscosity of the mixture. So it goes, when there is no water, here we have a viscosity of the oil, then goes up and you meet an inversion point, I, and then it goes down all the way when this is 100 or when this is 1, the viscosity of the water. Okay, right? Yeah. So that's what I'm giving here, the two, because we will see not to start, okay? We are not going to put all the complications, but with the life of the field, that well is going to produce more and more water, Okay, so its emulsion viscosity is going to increase. So we want to see also what happens in that case. Okay, and the way we're going to represent, they did some measurements in the lab and they generated these coefficients. I think we talked about the Richardson model some classes ago also. Okay, it's just an exponential model to represent these two curves, and the cutoff value is 60%. And here you have the bubble point pressure is 30 bar, so we want to be all the time, let's say 5% above this value. Okay, right? So now let's do our analysis. We want, from reservoir people, they say we want that well to produce 1700 standard cubic meter per day of oil, and initially it's not producing any water. Okay, just fluid, 1700. Okay, that's the target, Q target. And now we want to verify if the pump will be able to deliver that rate or not. Okay, remember all the time you have to use, it's like the pump is serving the reservoir development strategy. Okay, if the reservoir wants this value, then the pump or the artificial lift design has to serve this purpose. Okay, if it's not unrealistic. If they want to produce that rate, and that rate is the one that they need to for the profit of their project, for their recovery strategy, etc. So the kind of the task of the production engineer that is in charge of pump design has to be to honor, if it's possible, to honor that rate. Okay, so that's what we are trying to do. So how do you recommend to calculate the delta P of the pump for this case? Okay, what I propose, let's see if all of you agree, is I remove the pump out of the system. Okay. So here I have P suction and here I have P discharge. Okay, as I don't have yet a pump, okay, it's not defined yet, or at least I don't have any information about it, what is available. Okay, I just take the complexity out of the system. I say, okay, my pump, let's take it away, and let's just calculate what pressure do I need to bridge. Okay, so how do I do that? I go and calculate the available pressure at the suction of the pump. Okay, I have the rate, I have the Q, let's say, of oil. With the Q of oil, reservoir pressure, and the IPR, I can calculate the flowing bottom hole pressure with the IPR. Then I can move all the way to the suction. I have P1 and I want to calculate P2, right, on our equation. And I can calculate the P of the suction of the pump. Then I stop. And now I go from the wellhead, and we know that from the papers, or they say that they will be operating at a constant wellhead pressure. That's actually in the papers of Statoil. They say that the pressure is going to be 7 bar. Okay, they're going to be operating, because remember that depends on the processing facilities, that depends on the separator, and they are going to try to keep that pressure all the time at 7 bar. So I have the pressure, I have the rate, and I can calculate counter current. I have P2 and I can calculate P1, which is the P at the discharge of the pump. Okay, and with these two P's I can say the delta P of the pump that needs to deliver P discharge minus P suction at a rate of 1700 standard cubic meter per day. Okay, very simple. Or put it in some other graphical way. I'm calculating pressure versus Q. That will be at a wellhead pressure of 7 bar, and this will be, so this will be the pressure at the suction of the pump, sorry, pressure at the discharge of the pump, and this will be pressure at the suction of the pump. Okay, right, that's the way they should look like. And I want to produce this rate here, 1700, and I'm going to calculate the difference between these two. Okay, so let's do it. So we are going to do the analysis first for the first time. We will do it for some other times, some other reservoir pressures with depletion to see what happens. But let's start with initial reservoir pressure. The water cut, I'm going to say initially that it's not producing any water, so it's 0. Then the average density, how do you calculate the density, average density for a mixture of oil and water? Do you remember? You had to use the volume fraction, okay? So density of the mixture is equal to the density of the oil times 1 minus alpha of the water plus density of the water 1 alpha of the water, right? Okay. So I have already programmed that expression for you. And that's actually, yeah, I'm not sure, I think it's here, single phase hydraulic. Okay, average property, you give this shouldn't be water cut, should be actually volume fraction of water. Okay, so volume fraction of water times the property of the water, 1 minus the volume fraction of the water times the property of the oil. So this we can use to calculate the average density. So, what was the name? Avprop. The water cut, okay. And here we're going to make one approximation, okay. If formally, how do we have to calculate that volume fraction, water volume fraction? Do you know? Do you remember? We need the local volume rate, okay, right? But let's take that complexity for now out, okay? And we are going to say that the liquid, the oil, and water, just an assumption, okay? Assumption, but a very important assumption. The oil and water are incompressible. That means that the rate of oil measured at the surface is equal to the volume rate, the local volume rate at any P and T, okay, and also the water. And this is usually not such is bad approximation, but it's not so too bad for this heavy oil with low GOR systems, okay. But there is all the time some gas coming out of solution that causes that they are going to be different, okay, the rates. But for the sake of this exercise, we are going to make that means that the volume fraction of the water at the given P and T is going to be equal to the water cut. Okay, just to simplify our life. Otherwise, it will be too many complications, one on top of the other, and it will be more difficult for all of us. But just for this exercise, okay? Commercial simulators, they actually take that into account. Okay, they take the change in. Okay, so let's all of that story to calculate that. Prop, and here I need the water cut, I need the property of the oil, which is density, what we are calculating, and we have to lock this cell, okay, and water, and the property of the water, okay, and it should give you exactly the density of the oil because it's pure oil, okay. Now the viscosity, here we have to use our emulsion behavior, okay. I know that for here doesn't matter, it has to have only the viscosity of the oil, right? But I want, so it will be a function of the water cut. Remember, in reality again, it's function of the water volume fraction, but we are assuming that they are the same. So I think I call this a complicated name, I think. Emulsion. Richardson emulsion viscosity, okay? And it has the two viscosities, the volume fraction, the exponents, and the cutoff. A lot of things, but these are the two exponentials that I told you for both sides of the plot. I hope you remember that, and it already is forgotten and you don't remember. So what was Richardson? Emulsion viscosity. And here I need a lot of things. Need the viscosity of the oil. I block it. Viscosity of the water. I block it. Then I need the water cut. Okay, that's not going to be blocked because when I drag it down, I want it to change. The exponent of the oil, it's here. The exponent of the water is here on the water continuous region. And the cutoff, it's 0.6, okay, and that also has to be blocked. Okay, I save, and actually it does what it's supposed to give, 0.100 centipoise, the viscosity of the oil. Okay. Just to do some quality control here at the end, if you go all the way to the end, you have emulsion viscosity, and I have done, using that input, I have plotted for the whole range of volume fraction. Okay. And this is how it looks like. And actually the viscosity jumps, you know, from 1 centipoise, which is the water, all the way to 100. So a more practical way to visualize that is using this logarithmic scale. And you see that when it's oil continuous, and then you have to add some water, then it's increasing, 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 almost all the way to 1000 centipoise. Okay, and then after I pass 60, it's just going to go down, and then goes from 1 centipoise, okay, all the way to, I think it's like 3 or 4. Yeah. Is it okay? Do you want to take a break? Do you need a break? Yeah? Are you sure? Or you want to continue? Just straight. Huh? We take a break? 10 minutes? Yeah? Okay. Okay, so here is plotting on log scale, okay? So don't be why it doesn't look exactly like what we discussed before, because it's exponential, the model that we are using. So in a log plot is going to show just like a straight line, okay? And you see that actually it goes almost 1 order of magnitude, okay? Here is something like close to, I think it's 860 or something like that, centipoise. So actually it can increase quite dramatically when you add water, when water is dispersed in the oil, okay? This is oil, we are plotting it green, and then the water is just some droplets. Okay, and this is actually the opposite. You have water and you have some droplets of oil. Okay, very important issue, and to avoid that, they add some chemicals that they are supposed to stop this behavior, or at least to minimize it. Okay, but we are neglecting that part for now. So let's see, what do we have? Where were we going? So we had the effective viscosity, and then we have the total rate. Okay, the total rate, that's the value that is giving, is 1700. So I say 1700, and should be in red, which is okay. And if I have that, then I can begin to progress from the bottom hole all the way to the suction of the pump. Okay, so let's do that. The bottom hole, I use IPR equation, IPR PWF, exactly that's what I want. And here I need the total fluid rate, then I need the J, and reservoir pressure. Actually, this shouldn't be blocked, okay, because that's I'm going to pull down. So this one should be like that, and it gives me a flowing bottom hole pressure of 110 bar. Okay, there is then 120 bar drawdown in the reservoir. So how do I calculate Q of the oil and Q of the water?
According to the fraction?
Yeah, I use the fraction. So this times 1 minus the fraction. Okay, and this is the total minus the oil. Okay. Then P at the suction of the pump, we are going to use line P. Which one, 1 or 2? 2. Okay, let's see if that's how I call it, or maybe I call it, no, it is not line, it's P1, no, huh? P outlet, P out, okay, that's correct. So what do we need here? We need the rate, and remember here, in reality we should use the local rate, but we are assuming that they are the same, okay? But please take that into account. Total rate, oh, that shouldn't be blocked also, should be just like that. Internal diameter, that's this big diameter here, and that should be blocked. Then the density, I have it here. The viscosity, I have it here. Length, okay, we are assuming that it's a vertical pipe section. So length, where is length? This one, right? And that should be blocked also. Then theta, that's the angle from the horizontal, the angle of the pipe in this, and it's in degrees. That's all explained in the description of the function. So it's 90. Then P in, that's the flowing bottom hole pressure, and roughness is this value here, and that gives me 76. Anybody's quality controlling my work? Because if I were you, I wouldn't trust me so much that I'm doing things properly. Yeah, looks okay. Okay, so up to now I have done co-current calculations all the way to the suction of the pump. Now I'm going to do counter current calculations from the wellhead all the way to the discharge of the pump. And somebody was asking, you know, in the break, they say, okay, if we have the well, okay, and this is the platform, okay, and this is the seabed, and then from here there is going to be a hose, let's say 10 kilometers distance, all the way to the FPSO, and here I have my FPSO, okay, and this is, yep, here is where I have my set of separators, and this distance is 100 meters, okay. How is it possible that with 7 bar I will be able to actually flow the rest of the way? Okay, because it's 10 kilometers, I have frictional losses, the liquid is very viscous, and then I have 100 meters that I have to overcome to go up. So how is it possible? In reality, you don't use just the stream, but just collect all the production from all the wells, and you have a pump, you have a booster pump that is taking all the production of all the wells and then pumping it further to and this pump is actually making sure, pump makes sure that P at the wellhead stays all the time at 7 bar. Okay, so this is a booster pump. Okay, those questions are important. You all the time have to relate, and really a good way to see very quickly, you say, okay, 100 meters is like 10 bar for water, okay, and that really, you know, is quite a high distance, so that really, you know, there is something wrong here. Okay, so we are going now to do back calculation, and where do we have the wellhead here? 7 bar, that's given, and then I want to calculate the P at the discharge, and that, if we use the same logic, should be P in. Okay, and I have to put parentheses, P in, and this pressure, I have the rate that I don't have to block. The internal diameter is D2, that one I have to block. Density here, that is not blocked. Viscosity, length is almost 2 kilometers, and that one has to be blocked. Then I have, again, we are assuming that it's another vertical pipe, so 90 degrees. P out is 7, this value here, and then the roughness, that's another value that is going to be blocked. 185, are you getting the same values? Those of you who are 185 and 76, and here I calculate the delta P of the pump, that is going to be like 110 bar, 109 bar. Now so far, okay, so far what I have told you, what do I have to check if that operational condition is feasible or not? What's the only thing that I have told you? How they want to operate. That the pressure at the suction of the pump has to be greater than 30, okay, or 5% of 30. So is that fulfilling the criteria so far? Looks like, okay. How much is 1.05 times 30? Pressure at the suction has to be times 30 bar, okay. And how much is that? 30? 31.5. Okay. So far that fulfills that condition, but then I'm very concerned if the pump will be able to lift 100 bar. Okay. How do I know that without having much, I still don't have a pump curve, I don't know, but what could I do to know if that my pump will be able to lift that or not? Anybody has any idea? Remember, the electrical motor has a maximum power capacity. Okay, the electrical motor that I install with the pump. Okay, and usually, it depends on what the selection of motor. First, it depends on the size of the casing. Okay, if I have a very small casing, then there is no way I cannot fit a certain motor of certain size, certain capacity. Okay, so let's go like that.
But you can install a set of pumps.
Of motors, yeah. Power capacity, okay, and the casing size limits the maximum power capacity. Okay, and like you well said, you can put too many of them, but then if you have too many, then you make the axis too long, and that's also not desired. Okay, so you have also limitation on the number of motors that you can stack up. And also there is one important factor, that is money. Okay? If I want to put maybe a bigger motor, then if I have to say, let's say here in this field, I'm not sure exactly, it's like 30 wells, I think. But if you have to pay that amount of money times 30, then somebody is going to complain, okay? Because so it also depends on how deep your pockets are of the oil company, okay? And the range of power, they range maybe from 30 horsepower all the way. The limit is 15 horsepower, okay? 1500 horsepower. That's more or less the range, minimum and maximum power. Let's say that because of all of these constraints, the casing size, people say, okay, kind of a logical power capacity of the motor, if for this particular case, it's going to be 600 HP, okay, horsepower. That's the maximum that you can fit with that casing. That's the maximum that we can afford. That's for that rate. That's kind of a reasonable number, okay. That number came from the expert that you have to pay a lot of money to get this number. Comes from the expert. So really a way that you can verify, or you can use if your delta P and your Q are feasible or not, is to calculate the power consumption that you need to pump this fluid, right? And then you compare it with this 600 HP. If it's less, it means that you will be able to pump it. If not, it means that you won't be able to pump this rate, right? So how do I calculate? So now comes the other question. It's kind of a chain of questions, okay? How do you calculate the hydraulic power required to compress a fluid from P1 to P2? Anybody remembers? HYSYS? No, we want to use an equation that you saw in kindergarten, when you were very young.
But it has efficiency also.
Huh? Okay, it has efficiency, okay? You're going on the right track.
The denominator.
The hydraulic power is equal to
Q times delta P.
P2 minus P1 times the rate, okay? And that tells you how much is invested only in actually increasing the pressure, okay? But you have a lot of losses. Remember that the fluid, when it passes through the pump, it has to change direction. Also, if the fluid is viscous, it's also dissipating a lot of heat with all the impellers. Then you have also the electrical motor has an efficiency. So usually what you divide this by the efficiency of the pump, okay? The overall efficiency of the pump. And that's how we estimate how much power the pump is going to use. So now we enter into another problem, okay? We say, okay, we want to estimate that the power has to be less than 600 horsepower, but now I have a problem. Now which efficiency do I use? Anybody has any idea of the efficiency of a pump, of an electric submersible pump?
75%.
70%? Okay, typical values are between 50% and 70%. A very good pump might be 75-80%, but that's a really top of the top. You don't want to pay too much money for a pump like that, okay? So reality is between 50 and 70% efficiency. And that means that to achieve certain delta P is going to need 1 over 70 times 1 over 0.7 times more energy, okay, because the rest is going to be dissipated in friction, in all kind of losses, okay? So let's try to make that calculation for our, so we're going to assume an efficiency of 60%, assume of 60%, okay? I will tell you later what that efficiency depends on, but for now let's say this is the range from 50 to 70, so I'm going to assume an average value of 60, okay, and to calculate the power. Okay, power here is in HP, so do you remember the units? To get it in, we're working with the SI system, so we want to get it in maybe watts, and then we convert to horsepower. Okay, so which units should I use? Pascals and cubic meter and seconds, I think, right?
Second hour.
Huh?
Second hour.
What is a watt? We go again to kindergarten.
Joules per second.
Joules per second, and joules is Newton per meter, and Newton is okay, so we have P pascals times rate cubic meter per second. Let's see if that gives the, okay, pascals is Newton per meter, okay, second, and yeah, so I get from here exactly joules per second, okay? So I have to multiply in pascals, and the rate has to be in cubic meter per second. You see, these things, you use them, okay? You use them in your normal life. Okay, so let's see, P discharge minus P suction, that's in bar, so to take it to pascals I have to times 1 e to the 5, and then times the rate, and the total rate is here, and then the rate is per day, so I have to take actually 2 seconds, and that I have to divide by, is it correct? Like that? Yeah. Okay, and that's in that's in watts, and now I have to take from watts to horsepower. And how do I do that? Well, I go to my converter. I exhausted my mind, so I go to power watt to horsepower. Okay, this number. Okay, and what is missing here? The efficiency. Okay, we are forgetting the efficiency. So we have to put someplace the assumed efficiency. Okay, and that's going to be in just a fraction, and we are going to assume 0.6. And this value, and I block it. Wow, that's actually quite high. Okay, but it tells me still is below 600, so I'm happy. Okay, I'm sure I maybe I will be able to pump that rate or not, okay? But so far, with my very simplified analysis, it looks like the pressure, suction pressure, is greater than 31.5 and the pump power is less than 600. So now let's move to another pressure, okay? So how do we do that? Very simple. That's why we like Excel so much. 215. Let's take steps of 15 bar, okay? Water cut, we say again, is not going to change. We don't have any more information. And then I just drag all of that down, right? And if I didn't make any mistake, it should work. Huh? Here should be 1700. This should be 7, okay? The power is below 600. The suction pressure is above 31.5. So everything is nice and easy so far. Now we go to the next pressure, 200, 0. And I drag all of them down. Okay, 7 here and 0 here. Okay, oops, here I got a problem, okay? Here the suction pressure is still well above what I need, but the power is already hitting the upper limit. So how can I fix that? What can I do to fix what suggestion do you think?
Better efficiency.
Huh? Better efficiency, but the efficiency really is due to the machine, okay, that I'm going to put there. They reduce the rate, okay? So let's see if we try. So how do we reduce the rate in a smart way? Solver, okay. You're getting used to the hang of the solver. Then don't get too addicted, because then you won't be able to do anything without solver. Okay, so we say solver, please take this to 600. Okay, let's see if it works. I have not tried to do that by changing the rate. Okay, exactly to 600. Okay, so that means that for that reservoir pressure, according to my very simplified example, okay, I'm taking only power and I'm taking only suction pressure, but according to that, I will have to, at 200 bar reservoir pressure, I will have to reduce the rate to 1676. Okay, and we are going to use a curve of the pump, and we are going to show what other things do we have to take into account. Okay, should we continue the analysis for 175, for example? Yeah, that's going to be the next step. That's going to be for the homework, actually. Okay, 7, I don't know why this is changing, 76. Okay, and again I do the same. Actually the suction pressure now is 22. Okay, so what do? I have this is exceeding and this is exceeding. So how do I use the solver in that case? Huh? I can use a constraint, okay? So I can say that I want to send exactly 20 to a value of 600 by changing the rate, and I want that the suction pressure also has to be greater or equal than 31.5. Okay, and solver finds a solution. Okay, 32. So I got exactly, so see, I got exactly 600, the same power as before. Should we try one more time? One more rate, reservoir pressure? I think actually, I'm going to show you later the forecast made by Reservoir Simulator of one of these wells, okay? And we are going to see where we are and what. Okay, again, now it goes to 7, and I probably will have to reduce. Huh? Okay. That's good that you're awake. Okay, so it's 21. Wait. and 21. Okay, what happened here? Well, actually, remember here I think we're doing something wrong. Okay, we are forcing the power to be exactly 600, but in reality it could be less than that. Okay, what has to be greater than 32 is the suction pressure. Okay, so here I can reduce that. So what would be a better way to put it?
Set it as a constraint.
So maybe
I can say that this number has to be greater or equal than smaller or equal than 600, right? And but now what I'm maximizing or minimizing?
Maximizing the flow rate.
The flow rate. Okay, let's see if that works. So I'm actually maximizing the same variable. Would that work? Okay. 31.5. I think if I increase here, okay, 31.5, and we should repeat that also for the previous point. 20. I think the value will be exactly the same, but just in case. Okay. Yep, for some coincidence they reach at that particular pressure, they reach the same suction pressure. Okay. So we have done now a very rough analysis, but what is the conclusion of this analysis? Okay, what are we going to tell back to the reservoir engineers guy department? Okay, we're going to say actually that after this pressure you won't be able to sustain anymore 1700, and that's why, because of the pump power capacity. Okay, and in this case you can actually do something. You can try to install a bigger pump, or you can try to buy a kind of a higher capacity pump if it can fit. So actually here you can do something, but after that the problem that comes in this reservoir pressure is that already the suction pressure is reaching the lower limit, okay, of 31.5. So here there is really nothing to do. Okay, you cannot, maybe what would be maybe a suggestion, a realistic suggestion. What can you do to so this won't be an issue? Well, we could try, if you think, we could try to reduce the friction losses between formation and the suction of the pump, right? And how do we reduce the friction losses, or how do we reduce the losses? We can put the pump closer to the formation, right? So this depth that I gave you initially, 380, if we make it smaller and smaller, then we might be able to increase this pressure, right? A bit. But usually, especially in these inclined wells, okay, these deviated wells, all the time the basic or the common principle is that you try to put the pump as close as possible to the formation, without that you don't have problems later that it's going to get stuck by pulling it out or putting it in. Okay, so really the pump has to be all the time in the lowest point possible, as close as possible to the formation. Okay, in deviated section. So really, maybe there is something to do there, but generally that's common practice. You try to put the pump as close as possible to the formation. Okay, now let's go back to pump theory, a bit about pump theory, and let's see how we can, with this very rough analysis, how can we do a better analysis if we already have a pump. Okay? So I told you last class how the pump behaves. What is the delta P of the pump versus rate? Okay, looks like an IPR going down. And this rate, remember, this is the local rate, total liquid rate. This is local rate. And I told you that you can either, produce a very high rate with a low delta P, or you can produce a low rate with a very high delta P. And if you see the power equation that we have done, that relationship comes given by that. You see that if I increase this one, and I have this one is fixed, then this one has to go down. Okay? So really the line is giving you kind of the constant energy line. Okay? And this is for one rotational frequency. And if I change the rotational frequency, the pump, if I reduce it, the pump will deliver less. Okay? F2, F3, and F4. Or if I increase it, the pump will give more and more. Usually the limits of the rotational frequency, they are given in frequency and are something 60 to 65 hertz, and the minimum limit is 30 to 35 hertz. Okay, that's our typical values for the pump. So if we look at the points that we have plotted here, how are they going to look like in the map? Okay, if we are going to guess, okay, we are going to do it just right away. But how these points that we just plotted are going to look like? Okay, so let's try the first one. 1700. Let's say that is here. Okay, and we have the first point. Then the delta P is going to increase. Okay, and what happened in the third reservoir pressure? Remember that we tried 1700, right? And what happened? We didn't have enough power, right? So where the point was initially before I reduced the rate was probably here, right? Just outside of the curve, because it didn't have enough power to reach this point. So what did I have to do? I have to reduce the rate, okay, and be someplace here, okay, and then I was reducing further the rate, maybe someplace, and the delta P, how is it? Delta P of the ESP, yeah, I took it away. That was very smart of myself. 150, okay, remains more or less constant for the last 2 points, but the rate is reduced. Okay, so it's going to look, we think it's going to look something like that. Okay, just constant first going up, then I reach the limit in power, and then I have to reduce because I reached the limit in suction pressure. Okay, so ideally, how do you want to design? If you were, we are not responsible for in this exercise about choosing the pump, but if you want to choose the pump, what do you try to do? Did you choose, if you have, let's say your points are like this, okay? Your points are 1, 2, 3, 1, 2. Do you choose a pump that has this operational envelope? No. Do you choose a pump that has this operational envelope? No. You try to choose a pump that all the points, operational points, falls exactly in the center of this plot. Okay? That's kind of the philosophy of pump design. That for the life, let's say this change is going to occur in a lapse of 5 years. So in the life of the pump, most of the operational points where I'm going to be, they fall more or less in the center of the pump map. Okay? Now the story doesn't end up there. That clear? Yeah, so far? Yes? Okay. I told you last class that actually we don't plot for the pumps. The pumps are not plotted with delta P, but are plotted with delta H, okay, delta head. That is delta P divided by the density times the gravitational acceleration, okay, versus Q of the liquid. And if we have some pictures. Okay, so let's talk a bit about efficiency. I think I need a bigger page. Okay, so that's this head, that's curve that is set here versus flow rate, local flow rate. Okay, and what happens is that you see that these are the passages, what I showed you. Where is it? Okay, here. Okay, these veins, okay, these are the passages. If you see it from the top, are these passages, okay, and the way they are, the angle that they have, if the fluid comes exactly in this angle, okay, then it's going to flow smoothly between these channels. Okay, if it goes exactly in this angle. The thing is that this angle is only achieved at one unique flow rate. Okay, this angle comes given by a velocity, and a velocity is rate divided by cross-section area, right? So this angle, we cannot have multiple angles. Okay, we cannot mechanically rotate these angles to adapt it to the flow. Okay, they have to be fixed. Okay, so what happens is, in consequence, when I increase the angle, like if here, okay, initially here the fluid is coming like that, okay, but now the fluid begins to deviate because the rate is going down, and then when the fluid is deviating, all the time getting, you see here this area, a recirculation area. Now the fluid doesn't follow straight the path in between the veins, but it's actually creating some recirculation in between the veins. Okay, and what causes that? What is the consequence of that? Losses. Okay, loss in efficiency. So it's actually what this graph is telling us. Okay, if I'm exactly at this velocity, if I make exactly that the fluid goes at that angle against the veins, I'm going to get maximum efficiency. I will have just some frictional losses, and that's all. But then if the rate begins to decrease, okay, then the fluid is not going to impact the veins anymore in the proper angle. It's going to all the time decline and decline and decline, and I'm going to have the formation of these additional recirculation losses. Okay, clear so far? Yeah. And the same thing is going to happen if I increase the rate. If I increase the rate, it's going to happen on the other direction. Okay, and I will have a recirculation now on this wall here, and then the frictional, the losses will be higher and higher. Okay, usually because of that, when this happens, you get a lot of vibration. Okay, when you go away, so that's called the best efficiency point. Okay, so let's put it here. Best efficiency point when the flow is aligned with the vein angle, and that happens only at one unique flow rate. Okay, now if I increase it to the extreme, what I will see is that there will be a lot of vibrations, a lot of heating, and that causes some negative performance on the machine. Okay, a negative performance of the pump. So people, what they do to be on the safe side, they say, okay, please don't take it more than this limit, than this rate, and more than this rate, because in between these two, I can guarantee you a high enough efficiency, an efficiency between 50 and 70%. Okay, so they define, please, if you want your pump to be healthy, to have a nice life of 5 years, please try to operate. It will be the equivalent of our diet. Okay, please, you have to eat your vegetables 3 times a day and your proteins, etc. It will be the equivalent. Please try to operate within those limits. On those limits, they change depending on which frequency you are rotating. So I'm going to show you now the full picture, how the plot looks like. Actually, this, just to make a comment on this figure, these are actually, they put a rotor of a pump with transparent, and then they were actually looking at they were dropped some particles in the fluid, and they see how the particles are moving in between the veins. And that's how they got these pictures. A lot of work, but very interesting. okay, what is happening, because that's what the theory tells you. But to see someone measuring it is kind of amazing, that actually the theory represents so well the practice. Okay, so here we're looking from the top. Remember, the fluid goes from the center and then is distributed to the side. Okay. So actually, this is from the catalog. This is from PipeSim, and you see that you see for different frequencies. Here they have up to 90 Hertz, but you usually don't operate them such high speeds. Okay, and you see each one of them has a line. This is the minimum, the maximum rate line. You cannot operate. It's not recommended to operate greater than that line, and it's not recommended to operate less than this line. And these points are just the best efficiency points. Okay, and you see that each frequency has its own rate, best rate that has the best angle, incidence angle to these vanes. Okay, so that's an additional, to our point of view, that's an additional constraint that we have to take into account. We didn't take that into account, right, in our analysis. That for each frequency there is actually a minimum and a maximum rate. My flow has to be between a minimum and a maximum rate. Okay, yes?
Do we choose the frequency, or is it...
The frequency is something that I can change. Okay, I can control, if you remember last class, with a frequency variator. I don't know why this is so big. Okay. Okay, comes from the generation, from the grid, from a diesel generator, etc. You have a transformer, and maybe you need to reduce the voltage. Okay, and then goes to this box that is a variable speed drive unit, and that's changing, actually giving the same voltage that the pump needs, and then changing the frequency depending on the rotational speed that you need to have. So when you are in Brazil, you are in the offices, and you are just saying, okay, we have to update. So one thing that now maybe you can tell me, the points that we said was something like this, right? Going up, and then going to the left. What I have to do operationally in the pump with time? Change the frequency. I have to increase all the time the frequency, just like the choke, opening all the time the choke. In this case, I have to increase all the time the frequency up when it reaches a point where I have again to reduce it. Okay, so you're sitting here in the offices in Brazil having a nice life, going Copacabana, etc., and you say, okay, now the reservoir engineer told me I have to produce 1700. Okay, for this reservoir pressure that I have to increase the frequency. So you send the signal to the platform, this remote terminal unit, and it's going to say, please change the frequency of this electrical current that I have to, I don't know, depending on what I need. Okay, 40 Hertz, 45, 50, etc. Okay. Okay, so that's one thing that we didn't take into account, okay, these limits, and that's what we are going to look at tomorrow. How do we first calculate these limits, and how to take them into account by changing the rate. And then we are going to see that the performance of the pump actually depends also on the viscosity of the fluid. Okay, the pumps are usually measured with water. The performance is measured with water. But usually you have fluids more viscous than water, that you are dealing with fluids more viscous than water. So actually there is a decrease in the performance of the pump due to viscosity, and that has also to be taken into account. Any question? Are you going to forget this discussion for tomorrow or not? No? Okay, so tomorrow we're going to talk about more in detail about the pump, and we hope to close with that topic and go a jump to compressors. Okay? Thank you for coming.